Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, TIFR, Jest, IIT-Jam and other exams related to physical science. Okay. So this is the lecture number 12 of thermodynamics and statistical mechanics. Okay. And also guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science. Okay. And also guys, please share my lecture details to your friends so that they will also be able to watch my free live lectures and will be benefited from it. Okay guys, so let's get started. Okay, meanwhile just let me check whether I'm audible or not. Live lectures, and yes, I'm audible. I'll proceed further. Okay, so so first is mean free path, right? Okay? Mean free path, mean free path, mean free path. Yesterday we have studied density of state. Okay, phase cell, phase space, phase space, microstates, macro states, right? So now it's uh, mean free path we are going to study. So mean free path is denoted by lambda. Okay, and the value of lambda is lambda equal to 1 upon pi n d square, 1 upon pi n d square. Okay, so lambda is 1 upon pi n d square, n d square. Okay, and where d is dimension, guys, d is dimension, d is dimension, n is density. Okay, number density. Right, so this is the mean free path formula. This is without correction. Okay, it's without correction, without correction. Okay, next is after correction. After correction, after correction, lambda value is going to be 1 upon root 2 pi n d square. Okay, 1 upon root 2 pi n d square, 1 upon root 2 pi n d square. And also guys, we know that pressure equal to nkt, pressure equal to nkt, right? So from here the value of n is going to be kt upon p, right? So in place of n we'll write kt upon p. So lambda is going to be mean free path, lambda is going to be uh, this is here we have made mistake, so n is going to be p upon kt, guys, p upon kt. Okay, p upon kt. So we'll put the value. So lambda is going to be 1 upon root 2, 1 upon root 2, okay, into 1 upon pi d square, and in place of n we'll write p upon kt, p upon kt, this one, p upon kt, right? So this value is going to be, lambda is going to be kt upon root 2 pi d square into p. Okay, so kt upon root 2 pi d square into p, or from here the lambda is going to be proportional to t upon p. Okay, mean free path is proportional to temperature upon pressure. Okay, so this is important formula. Okay, P is the pressure, P is temperature. Okay, so this is mean free path, guys, and here lambda is proportional to, that is mean free path is proportional to T upon P. Okay, next, guys, so if we talk about this micro state and macro state, so we have this one macro state. I'll give the example. Okay, macro state, and this is for this particle. Okay, so this is for 4 particle we are talking about. Okay, 4 particle and 2 energy level. So 3 1 1 3 4 1 0 4 sorry 0 4 0 0 4 and 2 2 2 2, right? This is these are the my macro states for 4 particle. Okay, 4 particle and 2 energy level. 2 energy level. Okay, for this macro state, that is 2 2 macro state. Okay, this macro state we have different particle. Okay, distinguishable particle E, B, C, D. Okay, these are the particles. So we have to find the for this 2 2 energy level, right? We have to find the corresponding micro state. Okay, so the corresponding micro state is going to be, make box first. So here will be AB, CD, and then AD, BC. Okay, and ADBC. Okay, ABCD, ADBC. Okay, AC, BC, CD, CD, AD. Okay, and BC, AD, and BD, AC. Okay, so there for this particular energy level, right? For the 2 energy level and 2 particle, for this macro state, this particular macro states, there are 6 micro states, guys. Okay, for 4 distinguishable particle, 1 2 3 4 5 6. Okay, so this is the for this particular macro state, there are 6 microstates for distinguishable particle, which are A, B, C. Okay, so here classical particle, classical, classical particle, and quantum particle, guys. Quantum particles. Okay, classical particles are distinguishable particle. Okay, this distinct, distinct, distinguishable particle. So classical particles are distinguishable particle like this A, B, C, D. Okay, so they are distinguished. Okay, so classical particles are distinguishable particle. For example, A, B, C, and so on. If we talk about quantum particle, so they are identical particle. Okay. They are identical. They are identical particle. They are identical particles like A, comma A, comma A. So these are indistinguishable particles, right? Indistinguishable, indistinguishable particles. So indistinguishable particle, indistinguishable particles. So they are indistinguishable particles. Okay. So these are classical particle and quantum particle. Very important, guys. Okay. Next, there is a quantum condition. Okay, there is a quantum condition. Quantum condition is lambda equal to h upon p. Okay, so this is de Broglie condition, right? So lambda equal to h upon p. H is Planck constant, p is the momentum, and lambda is the wavelength. Okay, de Broglie wavelength. This is called quantum condition, guys. Quantum condition. Quantum condition. Okay, and so in this is a quantum condition. S is Planck constant. Constant. P is momentum. Okay. Okay, and in this quantum condition is in quantum condition. So size of particle is equal to de Broglie wavelength. It's de Broglie wavelength. Lambda is de Broglie wavelength. Okay, de Broglie, de Broglie, de Broglie wavelength. Okay, so size of particle is de Broglie wavelength. Okay, this is a quantum condition, guys. Okay, so h is Planck constant and p is momentum. P is momentum. Okay, so here lambda is, we can write lambda is h upon p, right? Or we can write lambda is p value is 2 me, right? 2 me because p square, because E equal to p square upon 2m, right? So from there p value is 2 me. Okay, this is the lambda in terms of energy. Okay, here this is important condition you need to know. N lambda cube, n lambda cube, n is number density. Okay, n lambda cube, if n lambda cube is greater than 1, if n lambda cube, okay, so lambda is de Broglie wavelength. Okay, n lambda cube is greater than 1, so in this is the case of degenerate. Okay, so this is degenerate case. Okay, degenerate case, degenerate case. Okay, so if this is if n lambda cube greater equal to 1, then this is a degenerate case. Okay, second is if n lambda cube is equal to 1. If n lambda cube equal to 1, this is quantum case. Okay, this is quantum case. Quantum case. This is quantum case. Okay, and n lambda cube equal to 1, this is quantum case. Next is n lambda cube less than 1. Okay, n lambda cube less than 1. This is the case of classical non-degenerate case. Okay, classical non-degenerate case. These conditions are very important, guys. You need to know now. Okay, these condition, so by with the help of this condition, you will be able to solve questions. Okay, so it's classical non-degenerate, classical non-degenerate, classical non-degenerate, classical non-degenerate, classical non classical non-degenerate case. Okay, so it's a classical case which is non-degenerate. Okay, classical non-degenerate case. Okay, now boson, guys, boson. I'll discuss boson. Okay, boson, bosons. Okay, so bosons having we already know it has a integral spin, guys. Okay, integral spin. Okay, so bosons have integral spin. Okay, for example of bosons are like photons, they are bosons. Okay, photons, comma phonons, photons, comma phonons, comma mesons, comma gravitons, etc. Okay, so these are uh, bosons, guys. Okay, they have integrals, and the important point for bosons are no restrictions, guys. No restrictions, no restrictions, no restrictions, or no restriction on these particles, no restrictions on these particles, no restriction on these particles, no restrictions on these particles to be filled, to be filled, to be filled in different energy level, in different energy levels, different energy levels. Okay, so so phonons. Okay, so there is no restrictions on these particles. Okay, no restrictions on these particles to be filled in different energy levels. So in different energy level, we can fill. Okay, so we can fill as much as we can, right? So because there is no restrictions on these particles. Okay, this is very important point for boson. This point is important in solving questions. Okay. Next is fermions, fermions. Okay, fermions. So fermions have we know, right? It has integral spin. Okay, half integral spin. Okay, half integral, half integral, half integral spin. Okay, so fermions spin. Fermions have half integral spin, guys. Half integral spin. Okay, and they follow the Pauli exclusion principle, guys. Okay, it's important one. So when we fill the fermions in the energy level, then at that time we need to use this We need to fill according to Pauli exclusion principle. Okay, so they follow Pauli. I'm just citing points. Okay, so Pauli exclusion principle. Exclusion. Pauli exclusion principle. Okay, so they follow Pauli exclusion principle. Okay, examples of fermions are examples. Examples of fermions are electrons, okay, protons, neutrons, etc. Okay, so these are the uh, fermions, guys. Okay, very important. Okay, now next point on fermions is fermions having same fermions having fermions having same intrinsic property, intrinsic property, intrinsic. So fermions having same intrinsic properties, fermions having same intrinsic properties can have sorry cannot have NLM. Okay, same for both. Okay, this is important. So fermions having same intrinsic properties cannot have NLM same for both. Okay, if you talk about two fermions having same intrinsic properties, so cannot have NLM same for them. Okay, so those the principal quantum number. Okay, uh, so these are those are the numbers, quantum numbers. Okay, so they all cannot be the same. Okay, so fermions having same intrinsic properties cannot have NLM same for both. Okay, I'll explain that as well. So suppose the S, we have S equal to half. If we have S spin is half, in that case MS is going to be plus minus half. Okay, so, so for MS value is plus and minus half. Okay, this is the one. Next is for classical and quantum particles. We talk about classical and quantum. Classical and quantum. Okay. So for classical and quantum particles, guys, if you talk about classical particle, they follow MB statistics. Okay, Maxwell-Boltzmann statistics. Okay, Maxwell-Boltzmann statistics. Maxwell-Boltzmann statistics. Okay, they follow, or in short, we can say MB statistics. MB stat. Okay, so they follow MB stat. Okay, or stat, SAT stat. They follow MB stat or Maxwell-Boltzmann statistics. Okay, and for classical particle, psi 1 2 value is psi 1 2, which is R1 R2, function of R1 and R2. Okay, so this is going to be phi 1 R1 and or phi R1, or we can write phi r1 into phi r. Okay, so this is the this is for classical wave function. This is the wave function. Okay, for classical particles. Okay, so this is psi 1 to r1 r2 is going to be equal to phi r1 phi r2. Okay. So if we talk about quantum particles are bosons and fermions, guys. Okay, the classical particles are this a distinguishable particle. Okay, classical particle, and this is quantum particle. So these are bosons, and fermions. Bosons and fermions are quantum particle, means they are also quantum particles. Okay, so the bosons are identical, and it means bosons are identical and fermions are identical. Okay, fermions. Fermions and bosons are identical particles. Okay, we cannot, or we can say indistinguishable particle. Okay, and these are classical particle. Okay, these are quantum particles. So boson and fermions are quantum particles, and boson follow that B statistics. Okay, this one Bose and Einstein statistics. They follow BE stat. I'm writing in short. Okay, BE stat. Bose Einstein statistics, and fermion follow FD statistics. Fermi Dirac. Okay, FD statistics. Okay, so FD stat. FD stat. Okay, so boson follow this boson Einstein statistics, and this fermion follow FD statistics, means fermion Fermi Dirac statistics. Okay, I have written in short. Okay, and if you talk about the wave function for boson, that is symmetric. Okay, wave function for boson is symmetric. Symmetric wave function. Symmetric wave function, and that wave function is 1 by root 2, 1 by root 2, this is psi 1 to r1 r2. Okay, psi 1 to r1 r2, psi 1 to r1 r2, r1 r2. Okay, so that is 1 upon root 2 phi 1 r1, phi 1 r1 plus phi 2 r2. Okay, this is not plus, guys. Phi 1 r1 and phi 2 r2, phi 2 r2 plus uh, phi 1 r2 and phi 2 r1. Okay, so this is the wave function psi 1. Okay, and for Fermi Dirac statistics, which is and for FD, I'll write for Fermi Dirac in next page. For FD, that is Fermi Dirac statistics in short. Okay, for FD stat, the wave function is wave function is antisymmetric. Very important, guys. These questions are asked in the examination. Okay, antisymmetric, and value of psi 1 to R1 R2, that is 1 upon root 2, okay, 1 upon root 2, phi 1 R1, phi 2 R2 minus phi 1 R2 and phi 2 R1, okay. So this is the wave function for Fermi-Dirac stat, okay, Fermi-Dirac statistics, okay. There is a minus sign, and here this is 1 upon root 2 phi 1 R1 phi 2 R2 plus phi 1 R2 phi 2 R1, okay. So these are the wave functions for classical, quantum, and quantum particles. So quantum particles are boson and fermions. Boson follow Bose-Einstein statistics, and fermion follow Fermi-Dirac statistics. Okay. Okay. Next is there's a question. Okay, I'm going to solve this question. So we have given two particles as a question we are solving. Okay, two particles. Okay, and four energy levels. Four energy levels. Two particles, four energy levels. Okay, two particles are given AB. Okay, and so for MB stat in MB static. Okay, so these are distinguishable particles. We'll use MB status. Okay, we'll use MB stat, Maxwell-Boltzmann statistics. Okay, and we need to find the microstate. Okay, we have to find microstate. Okay, so I'm going to solve it now. So this is, I can write here, four energy level E1, E2, E3, and E4. Okay, we have four energy levels. Two particle AB which are distinguishable. According to this Maxwell-Boltzmann statistics, we need to find out the microstates. Okay, possible microstates. So how we are going to find it? I'll tell you now. Okay, so this is, so we can write this A, B, right, and this is like this. So we can write B, A, and then this. Okay, we can write this one A dash dash B, and then B dash dash A. Okay, we can write dash A, B, this, then dash B, A, this, right, and then dash A, B, and dash B, A. Okay, and then we can write A, A dash B dash B dash A dash. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? Any mistake we have done? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the one. And one more is there. This is dash dash A, B dash dash B. These are 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are other as well. This is, I'm telling here, okay. So E1, E2, E3, and E4. Okay, E3. So here we can write AB together dash dash dash. then dash AB together, dash dash, then dash dash AB together, and then dash dash dash. So total, if you count, this will be 16, guys. So possible microstates for this two part in MB statistics, that omega is going to be 16, right? Like this. And there's a formula for it as well, guys. So you need to note down this formula. Okay. So omega, that is possible microstate, is number of energy level, number of energy levels, number of energy levels to the power number of particle. Okay, number of particle, number of energy levels to the power number of particle. Okay, so this is the formula, guys. Okay, this is the formula. Number of energy levels to the power number of particle, and so from here we can easily find out delta, that omega. So number of energy level are 4 and particle are 2, right? So this is going to be 4 to the power 2, and that is 4 4 the 16, right? So this is the answer. So by formula you can directly get it, okay? And you can get like this as well. So there are 4 particles, four energy levels and 2 particles. How we can arrange them? So what are the possible microstates? So these are the possible microstates, and this is 16 for this. Okay, this is by formula. This is we have done manually. Okay. Next is for so now same question. Okay, 4 energy level and 4 energy level 2 particles. Okay, same question. 4 energy level, 4 energy levels and 2 particles, and we have to get it by, we have to use, so in B stat means Bose-Einstein statistics. Okay, this is Bose-Einstein Bose-Einstein's Bose-Einstein's statistics. Okay, Bose-Einstein. So in Bose-Einstein statistics, using Einstein's statistics, you need to find out this one, number of microstates. Okay, for 4 particles, so there are 4 energy levels and 2 particles. Okay, so for that, using Bose-Einstein statistics, you need to find out uh, possible number of microstates. Okay, so I'll solve it now. So this is E1 energy level, E2 energy level, E3 energy level, and E4 energy level. Okay, so here, in Bose-Einstein statistics, we know that these are identical particles, right? Bosons. Okay, so so there are 4 energy levels, 2 particles, right? And using Bose-Einstein statistics, we need to find out possible number of microstates. So simple. So particles are 4 particles, and those particles are going to be A because identical particle, right? So particles are going to be A. Okay. So A can be here, A can be here, this can be black, right? And then A can be here, A can be here, this is black. Then A can be here, A can be here, this is black. Then A can be here, A can be here. Okay. Then A can be here, E can be here. No, 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 this is not correct. A can be here, A can be here. 1, 2, 3, 4, 5. Okay. So A can be here, and next is A can be here, A can be here. 1, 2, 3, 4, 5, 6. Okay. Or boson, we can fill any number of particle as well, right? So A can be here. This is blank. This is blank. This is blank. Then A can be here. This is blank. This is blank. Then A can be here. This is blank. And then A. Right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So for Bose-Einstein's statistics, okay, if we have been given 4 energy level and 2 particles, right? So in that case, the microstate, possible number of microstates, okay. So 4 energy level and 2 particles. The possible number of microstates are 10. Okay. This is the microstate. Now the same question for FD statistics, right? Fermi-Dirac statistics. So same question, that is 4 energy level, 4 energy level, 4 energy levels, 4 energy levels, 2 particles, 2 particles, okay, and by FD, Fermi-Dirac statistics, okay. So using Fermi-Dirac statistics, you need to find out total number, that possible microstate, or in short we can write FD statistics, FD stat, okay, FD stat, okay. So Fermi-Dirac statistics, we have to use Fermi-Dirac statistics, and we need to find the possible number of microstates, right? Same thing, 4 energy level E1, E2, E3, and E4. Okay. So here I will write, and particles are because in Fermi-Dirac these are quantum particles, identical particles, right? And also, guys, so we'll solve it. So we'll use Pauli exclusion principle. Okay. So this is going to be A dash dash, then A dash, okay, then A, A, then dash A, then dash dash A, A. 1, 2, 3, 4, 5. One more missing. So A, or then A, A. 1, 2, 3, 4, 5, 6. Okay. So these are 2 particles, right? So here for Fermi-Dirac statistics, the omega value is going to be 6, because 1, 2, 3, 4, 5, 6. Okay, so for Fermi-Dirac statistics, right? If we have given 4 energy level, 2 particles, for 4 energy levels and 2 particles, okay, the possible number of microstates according to Fermi-Dirac, using Fermi-Dirac statistics is 6. Okay, this one. Okay, guys. So this is the one. Yeah. So there is one question, guys. I'm going to solve it. Question is, so we have given that energy level. This is E1 energy level, and this is E2 energy level. Okay, and here we can fill only one particle, and in this energy level we can fill two particles only. Okay, and we have been given three particles A, B, C. Okay, A, B, C particles. Okay, three particles A, B, C. So now we have to use ABC three particle. We have been given. We have to use MB statistics. Okay, MB stats, MB stat. Okay, MB stats or MB stat, MB stat. Okay, and we need to find omega. That is possible number of microstates. Okay. So guys, there we have a formula, guys. First, I'll explain the formula. Formula is we have omega, possible number of microstate is n factorial upon n1 factorial, n2 factorial, n3 factorial, okay, and so on. Okay, so this is the formula, guys, which you need to note down. Okay, where capital N is total number of particles. Total number of particles. Total number of particles. Okay, and N1 is total number of particle in E1. Okay, total number of particles in E1, and N2 is total number of particles, in E2. Okay, so N1 is N is total number of particle, N1 is total number of particle in E1, and N2 is total number of particle in E2. So we have given this condition, this in this question, that in this energy E1 there would be only there can be only one particle. One particle can stay. Okay, and in E2 only maximum two particle can stay. Okay, so we have given three distinguishable particles using MB stat. We need to find omega, and omega formula for MB stat we have this: omega equal to n1 upon n factorial, n factorial upon n1 factorial, n2 factorial, n3 factorial, and so on. So there are, so here n1 value is n1 value is 1. Okay, and n2 value is 2. Okay, so we'll use directly formula. So from here omega is going to be this one, n total number of particles 3 factorial upon 1 into 1 factorial. In one there would be only one particle, right? 1 factorial into 2 factorial, because there would be two particle, right? And 2, so this is going to be 3 into 2 upon 1 into 2 into 2, that is 1 into 2 into 1, and that is 2 2 will get cancelled, 3. So the omega equal to possible microstate is 3. And how this is going to happen? Like this. Okay, n1 equal this is like this. We have three particles, and this one. Okay, so a particle can be here, then BC will be here. Second option is A here, BC here, A here, and sorry, B here. So possible microstates, right? B, this is AC, and C, this is E. In this way, so a number of total number of possible microstates are 3. This is the level, because it is given, guys, in question, right? In this energy level, only one particle can stay. In this energy level, maximum 2 particles can stay, right? So we have a formula. This is omega equal to n1 n factorial upon n1 factorial, n2 factorial, n3 factorial, right? N1, N2 are, I have already explained, total number of particles in E1, total number of particles in E2, and n is total number of particles, right? So this will put the formula, and manually also we can see we have 3 particles. So if you put A here, then 2 BC particle, 2 particles BC will be here. If you put B here, AC. So there are three, there are three uh, microstates for this microstate, right? Well, guys, I hope you have understood it. Okay. Well, so guys, I'm going to stop here, and also, guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physical science. Okay. And also, guys, please share my details with your friends so that they will also be able to watch my free live lectures and will be benefited from it. Okay, guys, thank you so much. Bye now.